the object is dropped from a vertical distance of 12 meters above the ground. Well, we know that whatever the initial energy is at the top, kinetic plus potential, will have to equal whatever the final energy is at the bottom, kinetic plus potential. But at the top, it's all potential energy. We've dropped it. The kinetic energy is zero. At the bottom, that's the zero potential line. It's all kinetic energy. Therefore, we can equate the potential energy equals the kinetic. The potential is mgh. The kinetic is half mv squared. We equate those two. And so half mv squared equals mgh. And so we notice that the masses cancel. And we're left with v equals, and it's root 2gh. And we put the numbers in, and we have 2 times 9.81. Now notice I'm using 9.81. It seems to be a more accurate number for the constant g. And if we're dealing with 3 significant figures, that's the one to use. You solve, and you get 15.3 meters per second. Try this problem again on your own. Talk through it. Now, this time an object is thrown vertically downwards. And so it's 100 meters high from a building there. And the velocity is 10 meters per second that it's dropped at, or thrown at. And the kinetic and potential at the top must equal the kinetic and potential at the bottom. And so we can notice that at the bottom the potential is 0. And we're left with a very simple equation that the kinetic and potential that is initial, right there, that's the initial, equals the kinetic that is final. So let's put in the various numbers. We have half mv squared plus mgh, that's the initial, will equal 1/2 mvx squared. Now the x is the unknown velocity, and all the masses cancel again. So make sure you take them out. And now I have an equation that's fairly simple. I have 1/2 v squared. I know both of those